With the fundamental theorem of calculus.
Had no fun.
And basically what that gave us is the ability to calculate the area under the curve algebraically. Okay? Now we move on to part 2. So we can have more fun. And it gets to make you more mental. Okay. Fundamental theorem of calculus, part 2. What is an integral calculate graphically? Remember, area under a curve, right? Okay, so this deals with making a formula for area in terms of calculus. Okay, so let's start out with what you do know. If I ask you to calculate the area of a rectangle, there's a formula for that, right? It is. In the terms that I have given you, length times width, right? Okay. How about a circle with the radius r? Okay. What's the area of a circle? Okay, thank you. Do we need to put others up there? Triangle, base and height. What do you get? Okay, you guys are saying the wrong thing on purpose to make me mad. Don't make me mad today. Imagine that's a trapezoid. Let's use your imagination. Right? Oh, what else might? Oh, here's one that you might see. Square. The square, Benny. Yeah, pretty much everything else is derived from that. So here's the point. Those are all shapes that we have formulas to calculate the area, right?
Yeah.
Okay. What do we add in calculus? Curves. Okay. No, the baseball bats add those. Okay. Lack of hydration adds headaches. Okay, thank you. Okay, number one cause of headaches, lack of hydration. All right, so the question would be, how do we write an area formula in calculus terms? So that's what the fundamental theorem of calculus is all about. So here's what we're looking at. Taylor, can you put that down, please? Okay, we are going to call this function f of x, whatever it is. Okay, the area is going to be a function of x, so the formula is going to have an x in it. Okay, so we're going to call that calculation a of x. What?
Is that like the book kind of called it?
Yeah, that's what the book calls it. We try to stay consistent there. And then we're going to start at some value and end at that an x value of some kind. Okay.
So the x value is a of x is the end.
So x can change, right? Because areas can change, right? We need something to plug in. So we have somewhere to start and we have somewhere to finish.
And the finish is what you plug into the a of x.
Right. Okay. So we've learned to calculate the area under a curve as the integral, right? Or an integral. What are our integral limits? From a to x. Okay, so the area equals, and then here's where some people get confused a little bit. Why is it t? I don't want to go into it, but just trust me. Can you trust me on that, why we put a T?
Yes.
The reason behind it is so that when we actually do that math, we end up with an X in the formula. Okay. So this comes into the formula, X. So this is our area formula in calculus terms. Okay. So again, insert any function in there, in for f of t. Insert a function here. Do the math, and it will give you an area calculation for that function. Okay, it's a formula. So and then remember what the fundamental theorem of calculus gives us. We can define antiderivative, right? So what you end up with here, based on the fundamental theorem of calculus, is your area formula. This is generalized. Okay, I'll show you some specific examples, but notice the T's gone, right? Well, what you end up with is, okay, let me,
It's just to make it look pretty.
no, it's not actually. And there's a big purpose for it. What you end up with is the antiderivative of f at t evaluated from a to x. Right? The next step for your antiderivatives, which equals that right there. Does that make sense now?
Yes. So it's just like a times.
Yeah, it can be. Yeah. We do apply it in different ways, so I'll show you some of those situations here. So that's the big picture area formula in calculus terms, right? No, this would be like we talked about here. Area is length times width, right? Well, area is f of x minus f of a. It's an area formula. We just have an x there because it's a function dependent on the x value that you're given in the function. Makes sense. Whereas the area formula is here dependent upon the length and the width of the rectangle, L and W. And you have two variables there. Now we only have one variable.
So this is just the same thing again there?
It's pretty close, but we're going to apply it in some different ways. Yeah. Okay. So one way is to ask you to write the actual area formula for a function. So let's see.
On the area formula code?
So remember, from the last slide, the area formula is just solving that out and having an x value in there. So you have the function, the parabola, right? T squared, and then you're going from 3 to some x value. So what's the antiderivative of t squared? Okay. Evaluated from? Okay. So the next step gives you the formula. X cubed over 3 minus 3 cubed over 3. Right?
Without that x
So
value.
your area formula is third x cubed minus 9.
Without that X value, we come out.
What?
Like, without knowing what the X value is, like, what does that do?
So this tells me, here's x squared, right? D squared. If I start at 3, whatever x value I end at, that's the formula. So give me an x value.
Oh, yeah.
7. Okay, so 7, the area at 7 is 7 cubed over 3 minus 9. Right. Does that make sense? So it's, again, an area formula based on whatever x value you choose. All right. Okay. All right, so I want to write down the actual fundamental theorem of calculus part 2, because it does give us some info that we need. Okay, again, we're doing area calculations, so we have to have continuity. Right here. This is how your book puts this.
What is that?
Assume f of x is continuous on an open interval, I, and that a is in that interval.
All right.
So we're not defining the endpoints of continuity. It just says you have some function, here's an interval where it's continuous,
So it's just.
and a has to be inside that.
Makes sense.
Okay, so I'm not defining the boundaries. Your integral, your area formula will do that for you. Okay. Then and we already wrote this down. Okay. So there's your conclusion. Okay. Again, you can write this. What's that saying? A of x is, okay, there's another way to write it. Okay, again, this is AP language. I suggest you write this right below it every time because it's a little more obvious. You can also write it verbally.
So the derivative would be
Basically. Okay, so any one of those three is good. Again, I suggest you rewrite it like that just because it does make it very obvious. Because that's what this is formatted as. Right? Here's a neat result. And this is one that AP uses most. This is how your questions usually presented from this theorem. So we go up. Okay, the derivative of a of x is what? Yeah, f of x. And we already wrote that down, right? But I just put the star by this because it's a very popular AP question. Like free response almost every year type of question. We'll look at some tomorrow. Okay. Indeed. Thank you, Teal. But you have no idea what I just said. Keep a note. In this case, when we're doing these problems, where we derive the area function, that the area function at A is 0. Think about it. It's directly related to that. Let me write it down for you. What's going on there? Yeah, there's no width, right? This has no, from A to A, there's no thickness in that shape, right? No width, so we have 0. 0 area, right? Because that's what we're looking at there. See, A, plug A in for X, A to A, okay? This is a very necessary result for us to make this happen without anything else here. Okay. Again, I will show you some examples. So there's your formula. There's the actual theorem. Okay. Again, most of you are science career-based. Get used to seeing stuff like this. All right.
What is that on the integral sign? That's the top number.
A.
That's an A too?
Yeah. So what am I plugging in for X?
A.
A. So I put an A in here. But this area from A to A is 0 wide. It's like going from 1 to 1. There's nothing there. So there's no area. That's why we get 0.
So what's is the question just asking what happens if you plug it in?
Here's how we use that. Okay. Okay. Let big F of X be the particular antiderivative of sine x squared, little f of x. Satisfying f at negative root pi equals 0. Yeah. They make this sound really hard, don't they?
Equal negative root cosine?
Quit complaining. It sounds hard, but it's really not. Okay? It's really not. Express f of x, big F of x, as an integral.
Is the f of x is an integral?
Yeah, so we want to have big F of x as an integral.
How do you define the problem?
What does this say? Big F is the antiderivative,
Yeah.
right? Is this right? Big F is the antiderivative of f of x, which is sine x squared, right? So you're basically going from English to math, interpreting, right? So big F is the antiderivative of the function. Put a t in there. Oh, come on, man. Again, the small details about why that's a t now. Just trust us on that. What are my favorite limits?
Negative square root of 5.
To what?
So negative square root of
X.
Oh, but I do.
F at A is 0. So A value, right? Okay, so your A value comes right from here. Goes right there. And then this is a function of X, so we have to have that X there. That's all I see him do. Do 25. Seriously. He's probably gonna bench press more than me. Not that that's saying much anymore, but there you go. Okay, so there you go. That's your f of x as an integral. Okay, it's pretty rare to see this question, but it's good to be able to work both ways by generating the area function. Okay.
It's a little big, but it's a very common, or at least
This concept is tested very common. I'll show you how they approach it most of the time. Okay? Does that make sense? Unless it's misstated. Okay. Here's a very common AP question. So if you can do these, you're in pretty good shape. So you'll be given some area function or formula in terms of an integral.
So let's say, is that L plus T squared?
1. No, you are not in multivariable calculus quite yet.
Is that next year?
That would be Calc 3 in most places. So no, not Calc BC. That would be like Calculus F, A, B, C, D, E, F. I'm just kidding. Okay, calculate A prime of X. For your response point, it's a very common question. Which one? Okay. A prime of X equals 1 plus
X.
X squared.
That's it?
Done.
Wow.
Yeah, you're, again, what are you're deriving an antiderivative, so this goes away, right? And your x is what we evaluate the function at. You still have to evaluate the integral. So you don't have to do any of the work. All you have to do is remember how to calculate the antiderivative. And the fundamental theorem of calculus gives us that result. Okay, makes it easier. Okay. Here's another What is A at 3? Or, let's try it. Because you don't know how to calculate that antiderivative yet. Let's say it 2.
0.
Yeah, A at 2 is 0.
Wait, we have to number the square root. So you just turn it into 1.
If you need to, you can write it out. But you see that these are the same. There's no width in that shape. So we have 0. What?
So, go ahead.
Just for the sake of curiosity, to find the antiderivative of a square root, couldn't you just set it to 1/2 and then do the power rule for antiderivative?
Well, you don't know. No. Because the problem is you have that function plus the inside function. We don't have a chain rule for integrals yet. Okay.
So if this says like A at 2, and it's like, it's a problem where it ends up being 0, will it give you that formula?
You'll be given this.
Will we give them that and says evaluate at A at 2?
Or a picture. I'll show you one tomorrow where they give you a picture and say that A of x is defined by what's in the picture. It's a bunch of triangles and half circles or whatever. Calculate the area from 2 to 3 and you have to do the geometric calculations tomorrow. All right, what about A prime at 3? Yeah, plug 3 in. The square root of 1 plus 3, that's not a squared. Squared. Root 10? Yeah, so the calculus is done right here. A little bit here, but these are kind of basic evaluate a function problems at the same time. Okay. So again, very common to see that. Okay. Now there's one more little thing we'll talk about, we'll be done. Not what I wanted to write. Find the derivative of Did we throw a little wrench in the works there? Yeah, we did. What are you saying? Dodge bullets.
What did I say, sine t?
Hey, have you seen that yet?
No.
X squared. Everything I've shown you has been x, right? Okay, so how would you deal with calculating the derivative of something as a function?
You have to do chain rule.
It's a chain rule problem, yeah. So the derivative is the sine, plug this in at x squared. And how do we deal with this inside?
Times x.
Times 2x, the derivative, that chain rule problem, okay? So always make sure,
So would it be that and then?
if you have a function inside there, like something different than x here, that you calculate the derivative of it,
If it was like 3x, would it be equal to?
times 3.
And then once if you're finding the area of the curve or something like that, would that all be in parentheses and then minus sine negative 2?
Yeah.
What's that?
Two questions. One would be g prime x squared.
No.
And then
this right here takes on that outside. This is the outside of the chain rule. Okay, so all your row you focused on for the derivative is this right here. You have the outside to derive, right? This is your inside.
Yes.
So you derive the outside, antiderivative of the derivative, right? Just disappears, by the way. Copy the inside, derive the inside. Okay. Yeah, I know it's a little bit confusing. Okay. Just because of the, again, I can tell you, I don't fully understand myself. Okay. So, I haven't looked into it very hard. Something I've just trusted that works. Sometimes you just have to trust things that work. What do you trust to work in the morning when you come to school?
The sun staring right
I'm going to trust that my car is going to start. Do you know how that happens? Can anybody in here describe to me how a car functions?
You see, it turns like what car?
There's part of the problem. What car is it? But in basic terms, do you know how a car works?
You turn the key.
Most of you do not. But do you trust it's going to happen? Yeah, you do. Hey, we don't know how this works exactly, but we need to trust how it happens. Know the process. It's like turning a key on a car. Just know the process. Okay? Questions? All right.
Those penguins getting out.
Here's the deal. So, right now, we have not scored 5.3, so that's all due tomorrow, right? Okay. 5.4. Good luck for that. They just have split it up. Again, we'll look at some more problems tomorrow, more AP focused, but this is stuff that you probably have seen today. This we'll look at tomorrow, the spiral.
Says all this due tomorrow.
It says multiple days, so I'm guessing it's
Yeah,
due tomorrow.
Have I struck you as somebody that has high expectations for you, but has been reasonable in working with you?
Yeah.
You can be honest there if you think no.
Yeah, 10 years.
No, that's not reasonable, see? See how I plugged that word in? Reasonable?
Well, how about just 2 weeks? That's pretty good.
It's not reasonable, because by the time you actually do it the night before it's due, you will have forgotten it. Okay, there you go, not reasonable.
50 days.
I live in Dodge. If it says,
It's gotta be Friday. And then keep in mind, at some point in the next 2 days, you're gonna have a unit circle quiz. And on Tuesday of next week, you'll have a chapter 5 midway quiz to check for understanding. Okay, so you got lots going on right now. Because I've been pushing things back because we've had some sicknesses in basketball, so we gotta take care of this stuff.
Everyone.
Okay? If you need help, just come see me, we'll get it taken care of.
Arthur, just have fun.
I'll be honest with you, I don't think I've put this up on Classroom yet. And if I have, the schedule's different than what's on Classroom. That's why I put all this up here. So I would trust this. Don't trust Classroom right now. It may be wrong. Yeah, that's fine.